Hello, this is Prescott Registers Lab 7 video lab report, which deals with a star orbiting a black hole. In this lab, we are asked to find the mass of this particular black hole from the star's mass and its positions around a small portion of its orbit. We are also given the black hole's initial position. By using the code from Lab 6, we can find this quite easily. We can find the net force, which is equal to the gravitational force of the black hole we are dealing with. I then plugged in the star's mass here, the black hole's initial position here, and I used a delta t equal to the number of seconds in one day. I then pulled out the star's data and used it to find the velocities of the star between each of the points with this chunk of code here. I then plugged it into the formulas in this area so that I could get the component forces and changes in momentum. Since F net equals change in momentum over time, I just set the components equal each other with parallel equal to this part and perpendicular component equal to this part. Now when I run the code, the red path is from the data that is given. Now the blue arrow represents the perpendicular component of the force, with the red being the parallel, and then the black arrow being the sum of both components, which is pointing towards the black hole. Now, printed at the end, we are given the mass of the black hole, which is much greater than the mass of the star orbiting it. Now, running the code with the arrows set equal to the change in momentum over time and its representative components, we should get a similar result, with the arrows equal to the corresponding forces. Mathematically, this is quite true, since the change of momentum over time is equal to the net force, so therefore its components are also equal to each other. This is true due to the fact that the force causes the change in momentum. So therefore, whatever change in force occurs causes a corresponding and proportional change in momentum, resulting in them being equal. They're just cause and effect. And the parallel components and the perpendicular components show how much that changes in each direction. Now to answer the what if, I did this by writing a separate code with the same star data and the same black hole data, as well as the same delta t. Now to get the same initial position and initial velocity of the star, I used the same star data file and just pulled everything out like I did with the Lab 6 programs. Now using Newton's second law of motion, I was able to write a program that could predict the motion of the star around the black hole, using the net force equal to gravity, since there's no other forces acting on it around the surroundings. Now running this data shows a path that is similar, if not equal to, the path shown from the data file given. Now if we have a larger black hole, the perpendicular component would be a lot greater, causing a narrower path for one, but also there would be a faster turnaround due to the parallel force. To try and get them equal to each other, pathwise, the net forces has to be equal. So the only net force is gravity. So setting each of them equal to each other with the gravity around the smaller black hole equal to the gravity around the larger black hole gives us this mathematical relationship between the products between the two masses. Now if we have a black hole with a mass of 5 times 10 to the 31, this results in the orbiting star having a mass as shown. Now plugging this in to my program should give us a path equal to the one seen before. As you can see, the path is still a little too narrow, showing that you can't easily predict the path.